All right, everybody, welcome to Chapter 11, which deals with the interaction of gases. And we're going to start with how we measure them. And let's start our exploration of gases by going underwater to visit the wreck of the RMS Titanic, one of the most famous shipwrecks ever, probably the most favorite. And we see this little guy here who is visiting the Titanic in a submarine. And the question we want to ask ourselves is, why do you need a submarine to visit the Titanic? And so the thing that we need to explore a little bit further is how deep underwater the Titanic is. And just to give you an idea of how deep this is, here we have a bit of a comparison, and here is the surface of the ocean up here, and the Titanic is right around here. It's a little, not quite that deep. It's 12,500 feet. It's about half as deep under the ocean as Mount Everest at 28,000 feet is tall. So we're talking pretty deep. And all this water that's over the top of the Titanic has weight. Water has a weight of about 8 pounds per gallon. Well, you're talking all these gallons of water. It adds up to a weight of about 6,000 pounds per square inch. That's a lot. So these guys up here in this little submarine, they're in that submarine because if they stepped outside, that pressure from all the weight of the water between them and the surface would squash them like a bug. So that's how it works with water. How does it work with air? Believe it or not, it works the same way. So this is our atmosphere. And our atmosphere, you can see, is about 500 kilometers. It's about 300 miles from Earth's surface all the way to the edges of outer space. And while air is not as heavy or dense as water, it definitely has weight. And all of this weight of air between the surface here at what we call sea level and the edges of outer space causes this air to have weight. We call it air pressure. We don't really notice it anymore because we are used to it. But people who live here at sea level, hey buddy, they experience greater air pressure than people who go to the tops of mountains. And that's why when you go up in an airplane, which is, right around 30,000 feet, your ears pop. Well, that's because there's less air pressure. In fact, airliners like 747s have to have pressurized interiors so that you don't, die of oxygen deprivation because the air is so thin up there. And if you climb to Mount Everest, which is about 30,000 feet, you'll notice that it's difficult to breathe, a lot less air. And your eardrums feel weird because there's less air pressure pushing in on them. You're used to it here at sea level. And interesting, Wheaton is not quite at sea level. If we did a search on Wheaton, Illinois, we see that its elevation is at 748 feet above sea level. So we're not quite at sea level. Go to California and you are. Go to Denver, Colorado, and you're a mile above sea level. But right here around Wheaton, we're pretty close to the surface. So how does this translate to air pressure? All this weight of all this air pushing down on you at sea level, slightly less at the top of a mountain, more at Wheaton, but slightly less than it would be at sea level. How does this work? And so what we're going to take a look is how we measure air pressure. This is a picture of one of the first barometers. It's a word that's spelled barometer, and its whole purpose is to measure air pressure. to measure the weight of air pushing down on it from all the atmosphere between it and outer space. Well, how does this work? In this dish, we have a basin full of mercury. Mercury is pretty toxic, and so this was invented quite a bit before we found out how poisonous toxic was. And it was invented by a guy named Torricelli, one of Galileo's students. We're not going to worry about the date so much. This is in the 17th century. Galileo was 16th century, so this is right around late 1500s, early 1600s. And what Torricelli discovered is that for some reason, if you build a barometer like this with a big dish full of mercury, the pressure from air pushing down on the surface of the mercury in the dish will actually push this mercury up this glass tube to a height of 760 millimeters of mercury at sea level. And so what we've come to describe air pressure at sea level is that it will support this column of mercury 760 millimeters high. If you went to Denver, Colorado, where there is not as much air, it wouldn't be able to push this column of mercury quite so high, maybe 600 millimeters of mercury. So the millimeter of mercury became our first unit of air pressure. And all I'm going to ask you guys to be able to do in this section is to be conversant with units of air pressure. And so here we go. This is what we're talking about. And so scientists around the world call standard pressure at sea level 1 atmosphere. We're going to abbreviate that ATM, and that's our standard consideration for air pressure. What this means is that at standard sea level air pressure, the units we're going to use look like this. 1 atmosphere is the equivalent of 760 millimeters of mercury. We're going to use another term to describe millimeters of mercury because that can be a little clunky. So we're going to abbreviate it TOR, which is short for Torricelli, the guy that invented the barometer. And there's one more unit that we're going to use called the kilopascal, which is a standard metric unit. If you go to Italy, anywhere in Europe, and you ask how much air pressure goes in my tires. In the United States, we usually say 35 psi. They have no idea what you're talking about. They use something called kilopascals. For reference, standard sea level air pressure in psi is 14.7 pounds, quite a bit less than the 6,000 pounds at the depth of the Titanic. So the units that we want to be familiar with, 1 atmosphere is the equivalent of 760 millimeters of mercury, otherwise known as 760 torr, which is the same as 101.3 kilopascals, and these are all at sea level. If you go higher than this, these are lower. If you go to Death Valley, these are higher. But these are the units that we want to be familiar with. So here is the kind of question I'd like you to be able to answer for me. Okay, please convert 1,000 millimeters of mercury to both atmospheres and kilopascals. So let's do this first one. Let's go from millimeters of mercury to atmospheres. And we're going to say, all right, here's what we're trying to find. How many atmospheres is the equivalent of 1,000 millimeters of mercury? So we have an unknown and we have a known. We're trying to go from millimeters of mercury to atmospheres. We know that 1 atmosphere is the equivalent of 760 millimeters of mercury. So multiplying across the top and dividing by the bottom as we do, we get 1,000 times 1 divided by 760 is 1.32 atmospheres. Easy peasy, right? Let's do this next one. how many kilopascals is 1,000 millimeters of mercury? Some people like to convert to atmospheres and then to kilopascals, but you can do it all in one shot because you know what the equivalent at sea level of millimeters of mercury to kilopascals is. You know that 760 millimeters of mercury is equivalent to 101.3 kilopascals. So we're simply going to multiply across the top and divide by the bottom. 1,000 times 101.3 divided by 760 is 133.3 kilopascals. And that's all I'm asking you to try. All right, have a good one, and I'll see you on the next one.